today we'll be talking about machine learning and focus on supervised machine learning, especially linear regression, the simple ones. Now, machine learning can be broadly classified into three categories: supervised learning, unsupervised learning, and reinforcement learning. Supervised learning is where a model is trained using labeled data. It learns from past examples to predict future outcomes. One such method is linear regression, which we shall talk about later on. Unsupervised learning has no labeled outputs. The model identifies patterns and structures on its own. Now, there's going to be a future lesson that will cover one unsupervised learning analysis, and this will be principal components analysis and factor analysis. And then finally, there's reinforcement learning, which involves learning to trial and error with rewards guiding the model's behavior. This course will be focusing more on linear regression. So for starters, let's talk about functions and graphs. A function defines a relationship between x, the independent variable, and y, the dependent variable. Some key points. There are two perpendicular lines, the x-axis, which is the horizontal axis, and the y-axis, which is the vertical axis. The point where they intersect is called the origin 0, 0. Points are represented as xy coordinates. F of x is some function that gives one value of y for every given x. And here, the red curve is the graph of a hypothetical function f of x. In a linear function, this relationship is represented as y equals a plus bx, where b is the beta or the coefficient of x, and a is the alpha, the constant or the y-intercept, the value of f of x when x equals 0. For example, given the following data for x and f of x, we can create a scatter plot in Excel and ask Excel to draw a trend line and the equation of the trend line. Here, a equals 1, the value of y when x equals 0. And beta is equal to 4 since it is the coefficient of x given the standard form of the function. Now, suppose we can observe two sets of returns, one for a general stock index x and another for a particular stock y. The question might be, 1, can we relate the movement of the stock every time there are movements in the index? And 2, is there a linear relation between the two? Again, we can ask Excel to draw a scatter plot of x versus y, which we shall do in the exercises later. Then ask it to create a trend line and show the equation of the trend line. What is actually happening here is that Excel is creating a line that will go to the dataset such that the distance of the actual y's versus the line is such that the squared differences, when you sum it all up, would be a minimum. So visually, something like this is happening via what's called OLS, or ordinary least squares regression. We can also ask Excel to output a linear regression via the data analysis TOOLPACK found in the data menu. Note, it has to be installed and it has to be shown in the menu. The output will show the coefficients that are exactly what is shown on the trend line. That's how you can check if you did the right thing. Now here, the p-values are also shown, and the test is that the computed coefficients are equal to 0, meaning when we run a linear regression, we test if the coefficients are different from 0 or not. Here we note that we accept the null hypothesis for the intercept, meaning that the coefficient, the constant, is no different from 0. However, we reject the null hypothesis that the beta is 0, indicating that beta is significantly different from 0. Taking a look at the ANOVA results, we know that we reject the null hypothesis that the means of both residuals and regression are the same, indicating that the regression results are significant and different from the residuals. Now, that's important because that means the regression is in fact meaningful, and it's not some sort of what's called white noise that is expected for the residuals. Now here, we also take a look at R square. We note that the number is pretty high. And this means that it's a very good fit. The explained variation is around 85% plus. So going back to the questions, to answer question number one, we say yes, it looks like there is a positive relationship between the stock and the index, and both are increasing with time. And to answer number two, yes, the relationship can be assumed to be linear. Per movement of the index returns, there is an associated linear relationship to the returns of stock Y. So in finance and investments, linear regression models abound, and there's a well-developed literature that uses the statistical language to talk about investment topics, alphas and betas of investments, where beta might be a measure of sensitivity of a stock to market returns, for example. Alpha is the measurement of an investment manager's value or contribution to value. It also talks about how to put together a portfolio, taking a look at correlations of stocks. And therefore, this is something that we shall talk about in a while. So applying the model. In this case, we can interpolate what kind of returns are expected from stock Y given the expected returns of the index. So if the index return is expected to be 10%, then the stock is expected to return 10.71% given this formula. Note that I've used alpha equals 0 because it's not significantly different from 0. So I'm just really taking a look at the beta. In general, every movement in the index is associated with a 1.0711 movement in Y, meaning the stock's beta is greater than 1 and is thus expected to move more per movement in the market index, meaning it's riskier than the market index in the terminology of investments. So if beta were the same as 1, then the stock would be as risky as the market index. And beta is a widely watched number for stocks in the equity market. Linear relationships. In this case, we are talking about co-movement between X and Y. So notice that we're moving away from what we called univariate cases before. We were just talking about one set at a time. And we're moving now to what's called two variables or the bivariate case. Beta, for example, discusses how much Y moves per movement of X. So we're now associating co-movements of one variable versus another. So when we move from individual variables or the univariate case to two variables, we are talking about average co-movement. So we now introduce covariance, which is some sort of average co-movement between X and Y from their centers. The formula can be broken down into basic factors as shown in the table. So the product will only be positive if both factors are positive or both factors are negative, meaning positive times positive should be positive and negative times negative is still positive. It's going to be negative if at least one factor is positive and the other has a different sign. Therefore, covariance gives the average co-movement of one variable with another variable. If the covariance is positive, then on average, when X goes up from its mean, Y also goes up. When X goes down, Y also goes down. If the covariance is negative, then on average, if X goes up from its mean, then Y must go the other way down. Or if X goes down from its mean, then Y also goes the other way up. Standardizing the metrics. Covariance is a good starting point of measuring co-movement since it gives the relationship of how X moves about its mean at the same time Y moves about its mean. However, it is dependent on the unit of measurement. To normalize the metrics, we divide the covariance by the standard deviations of X and Y, similar to the argument for having z-scores in our previous lessons. So if we divide the summed up factors by the standard deviations of X and Y, we notice that it's similar in form to the standard score z. In fact, what has been done here is to standardize the covariance relative to the standard deviations in terms of x and y. And this is actually a name. This is called the correlation coefficient rho, or just simply R. If R is greater than 0 as you move through the axis from left to right, your y plot moves from bottom to top. So as x goes up, y also goes up. And there's perfect positive correlation if R is equal to 1. On the other hand, if R is less than 0, as you move through the x-axis from left to right, meaning your x becomes bigger, your y plot moves from top to bottom. So as x goes up, y goes down. So this is negative correlation. And if you have perfect negative correlation, R is equal to -1. Now, the correlation coefficient R, we have to remember, just talks about linear relationships. If the relationship is nonlinear, R may lead us to believe that there is a poor relationship when R is low, when in fact there might be a strong but nonlinear relationship between x and y as illustrated below. Also, the presence of distinct homogeneous groups can distort the meaning of R, creating strong pseudo-relationships, meaning on the left side, we might have a linear regression like so, but actually, since there are two groups, it might be better to take a look at the different clusters and doing separate regressions for those two clusters. So this may entail the use of cluster analysis or other unsupervised machine learning algorithms before doing any kind of regression. So now we have the univariate statistics of x, of y, and of x versus y in terms of the potential linear co-movement between x and y. Notice that the goodness of fit r squared is precisely just squaring r. Incidentally, beta is also related to the correlation coefficient rho and will follow the sign of rho. Beta is actually defined by the covariance divided by the variance of the x-axis as shown in the formula. Knowing the formula of correlation coefficient rho, if we multiply rho by the standard deviation of y and dividing it by the standard deviation of x, we get exactly beta. So we can extend the discussion of positive and negative rho with positive and negative beta to know how the line will move from left to right. And thus we get these computations for beta. We shall have more courses on the data science side in terms of problems using machine learning, using both unsupervised learning and supervised learning for data analytics issues. For these future courses, this course will be the prerequisite for the greatly expanded courses being planned. As usual, we will follow our game plan and introduce other crash courses similar to this course in the future. Meantime, we hope that you've learned a lot, and please feel free to give us your comments on future videos you want us to tackle. Please also like and subscribe to our channel to give us support. Thank you very much and see you again soon.